like to thank the organizers for inviting me to give this talk. So today I'm going to talk about a relatively recently discovered relationship between seemingly two different areas of research, both of which have over the years independently been studied for over 50 years. And only recently has it been realized that they're basically the same area of research. What I'm going to talk about is the relationship between these so-called soft theorems and how they're related to asymptotic symmetries of flat spacetimes. Not Minkowski, asymptotically flat spacetimes. I'm only going to be talking about this relationship in a particular context, but the full story is in fact even more richer because both of these are related to a third object, which has also in fact been studied for over 50 years, known as memory effects. So what I'm going to say is mostly going to be out of these two papers, worked on with my collaborators Templehurst, Slava Lysov, Andy Strominger, and myself. Okay. So this triangular equivalence of these three subjects, I'll explain what each of these are. This triangular equivalence of these three subjects seems to be very universal and applies to a large class of theories in physics: gravitational non-gauge theories, supersymmetric theories, and so there's a lot of applications. This will be a quick mention of what the possible implications are of this triangle. So if you're a string theorist or a high-energy physicist, you might be interested in quantum gravity. And one of the first things one likes to understand in quantum gravity is what the symmetries of the game are. So that's what this part of this triangle helps us understand. So symmetries of quantum gravity. This was one of the first steps that was also needed to understand in the ADS-CFT correspondence in order to understand what a quantum theory of gravity in ADS space would look like. More interestingly, I guess, it has recently been shown that the existence of these asymptotic symmetries plays a role in the black hole information paradox. This is certainly one of the most interesting questions in theoretical physics these days, how you can solve the black hole information paradox, and we've seen by work by Hawking, Perry, and Strominger how these are important. On this side of the triangle, if you're a field theorist who does experiments at the LHC, what is interesting is, so these soft theorems govern the infrared behavior of all of these S-matrix amplitudes. So in particular, what's known as LHC jet physics, or just the infrared behavior of, or what's known as SCET, soft collinear effective field theory. This is just a program to organize the infrared structure of QCD. And also another recent development is the amplitudes program. And it seems the existence of these symmetries interpreted as soft theorems, which I'll talk about in some more detail, can tell us some interesting consequences for these objects over here. Memory effects are more experimental, so if you're an experimental person and you would like to measure what I'm trying to say here, that's what memory does for you. So these give you various experimental measurements, and they also have experimental, if you're doing gauge theories, you can do an experiment at the LHC. If you're interested in general relativity, there are measurements in the sky. That can be performed, which can measure all of the effects that I'll be talking about here.
Are these existing measurements, the number two, or proposed
No,
measurements? Proposed measurements.
These are all proposed measurements.
Yeah.
So one of them for the memory effect, the most well understood memory effect is the Christodoulou memory effect, which was first described by Zeldovich and Prahar in 1974. The hope is, I guess, well, in LIGO, with the gravitational wave measurement, the wave has come through. So this effect is like a DC effect. The way a gravitational wave is measured, you have these two mirrors. So the wave passes and the mirrors oscillate. And the effect, the memory effect, is that after the gravitational wave passes through and everything settles, the mirrors would end up settling at a different distance from themselves as originally. So it's an overall DC effect. At LIGO, this would be hard to measure because they're put on pendulums, so eventually there's a restoring force which will put them back to where it was. But the hope is that you can measure it in ELISA because they'll be on inertial geodesics up in the sky. So that might be where you may measure them. Haven't been measured yet. Okay. So this general structure is very interesting and it kind of appears everywhere. I won't have time to talk about all of it. I'm going to talk about just one part of it in the context of GR, because this is after all a GR conference. I'm going to just talk about this part of the triangle. And in particular, the symmetries that I'll be talking about are what's called BMS supertranslations. And the soft theorem that I'll be talking about is Weinberg soft graviton theorem. So this was discovered in 1965. This was discovered in 1962. And just for completeness, I'll mention that the memory effect that corresponds to these particular BMS ones is the Christodoulou memory. Which was discovered which was written down in 1974. So these are all independently studied subjects for a very long time, and only recently have the connections been understood.
Not 1974, it must be 1994.
1994?
Yeah.
Well, this was first not by Christodoulou himself. It was first written down by Zeldovich and Prahar in a different form, but they were actually talking about the same thing.
They disagree that it's the same thing. They disagree it's the same thing. You ask Christodoulou.
Okay. Okay. Any questions so far? So what I'm going to do in the talk is explain what this is, explain what that is, and then explain what the relationship between them is. Okay. So what is Weinberg's soft graviton theorem? So as I said, this side was the field theory side of it. So in field theory, we like to study scattering matrix amplitudes, which is simply the amplitude, or rather the probability that a given set of initial states, you send in some initial particles, they interact in some complicated way, which highly depends on what theory I'm talking about, and then some new set of particles come out. And the Weinberg soft graviton theorem applies to an amplitude in which, in addition to all bunch of particles, there's also a graviton that's coming out. So let's suppose this graviton has momentum q, and it has some polarization epsilon mu, traceless symmetric. And let's give these guys some momenta p1, p2, all the way to pn. So this diagram is just a Feynman diagram. There's a number associated with this diagram that you can compute. And Weinberg's soft graviton theorem is the statement about the structure of this function, which is a function of all of these momenta, in the limit when q mu goes to 0. That's what the word soft means low energy. So it was proved by Weinberg that when q is very small, the amplitude factorizes into one term which is known as the soft factor. Let me write it down. second factor is just the original amplitude itself without the soft graviton. And there, of course, then there are further corrections which are order q to the 0. So this is the statement of Weinberg's soft graviton theorem. You have a scattering amplitude with an outgoing soft graviton, outgoing graviton. In the soft limit, you end up with a factorization of this form and multiplied by the original amplitude without the graviton itself. And there are higher order corrections which you can keep track of. As you can see, this term blows up as q goes to 0. It's typically called the Weinberg pole because it has 1 over q pole. There are subleading terms which are in fact also of interest and have soft theorems of their own associated with symmetries of their own. In fact, they're probably more interesting because there seems to be Virasoro, some two-dimensional CFT hidden in those, which is interesting for quantum gravity. I wouldn't have time to go into that. Okay. Certain interesting properties of this is that it's completely universal. It is independent of what interaction goes in here. You can write down any theory, as long as it's a theory of gravity, of course. We have a graviton. Any theory of gravity with any kind of properties, any kind of interactions, and you will always have this kind of factorization. Okay, any questions?
But when we say any theory of gravity, what does it mean? I mean, so that's maybe
you can write down any Lagrangian with any
Lagrangian which what? Which contains a Einstein part, probably, right? Or
which contains the standard Einstein term, which will be the kinetic term, and then you can add any higher derivative terms of your choice. And none of the higher derivative terms affect this leading factor. Probably doesn't even affect the subleading factor, as we have more recently understood. The terms beyond that are not necessarily subleading. They're not entirely understood yet, but certainly this was understood back in 1965. Okay. Whenever we see something that's so universal, independent of theory, we often like to attribute. It's good if you can attribute it to a symmetry, and as we will see, that's basically this symmetry right here. So let me now explain what is BMS supertranslations. So BMS supertranslations are, let me say the sentence first and then explain words in the sentence, is the asymptotic, BMS, the BMS group, of which supertranslations is a subgroup, is the asymptotic symmetry group of asymptotically flat spacetimes at null infinity. So let's explain what all of these words mean. So, as we all know, asymptotically flat spacetimes are governed by a Penrose diagram, which looks like this. So you have various parts of this Penrose diagram. There's a square plus, which is future null infinity. That's where all null geodesics end. There's a square minus, where all null geodesics begin. And I'll mention these others, though they won't play an important role. There's time-like future and past infinity, where time-like geodesics start and end. And then there's also spatial infinity. So this is just the basic structure. So it was... So let's set up some coordinates and conventions for our use over here. So there's a null direction over here, and I'm going to call that coordinate u. It's a retarded time. There's also a null direction near scribe plus. I'll call that v, retarded v. And we can introduce another coordinate r, such that constant r surfaces look like that in the spacetime. So when the r goes to infinity limit, I'll end up on square plus or on square minus, depending on how I've taken the limit, whether I've kept u constant or v constant. And of course, this is a Penrose diagram, so each point on this Penrose diagram is itself a two-sphere. So I'm working in 4 dimensions right now, though the story can be extended to higher dimensions. So each point on this Penrose diagram is a two-sphere, and I'll set up stereographic coordinates on the sphere such that each point is labeled by two complex coordinates z bar. Okay, so
Y2?
why?
Y2 coordinates?
Oh, this
Four complex.
z is one complex coordinate. Sure. Okay. Okay. So of course, it's a rather complicated story to study what in fact defines asymptotically flat spacetimes, that is, what is the appropriate fall-offs, and I won't go into the details of those things. I'll just mention what is I'll just tell you the definition. So the definition is simply the statement that the metric takes the following form near scri plus, and there's an analogous discussion near scri minus, which I won't discuss for now. So near scri plus, I have the structure. Remember, scri plus is r goes to infinity, so I'm going to do an expansion in large R. This is ground metric on a sphere. Yes. So this is just the metric of Minkowski spacetime. So if the spacetime I was discussing was completely flat, this is what its metric would look like in the coordinates that I've set up here. But of course, asymptotically flat spacetimes, there are subleading corrections in the large R limit. Let me mention just a couple of them, which will be of importance here. So this is what's known as the Bondi mass aspect. You may notice this is what appears for the Schwarzschild spacetime. MB is just the total mass of Schwarzschild. For a more general spacetime, this doesn't have to be a constant. It can be a function. All of these guys are functions of u and z bar. And another correction, which is and further subleading ones, but they won't be of importance. This is important because, as you may notice, this is the ZZ component on the sphere, so it's transverse to the null direction over here. So C, as we will see, is closely related to the CZZ and CZ bar Z bar. These two functions are closely related to the two polarizations of a graviton, of a gravitational wave. And they're transverse to the direction, to the null direction in which gravitational waves flow. Okay, so this is just what I mean by asymptotically flat spacetimes near scri plus. Any questions about this? Okay, just to be clear, Bondi, Metzner, BMS, I should tell you who BMS stands for. BMS stands for Bondi, Vandenberg, Metzner, and Sachs. So they worked out that almost all asymptotically flat spacetimes of physical interest, what they were looking for is isolated systems, such that you have like galaxies and stars and stuff like that. But once you go far away, everything becomes, there is no matter extremely far away near infinity. And they showed that all such spacetimes of interest take this form near scri plus. Okay. Okay, now what is the BMS group? The BMS group is simply the set of all diffeomorphisms that preserve this structure of the metric. So that's just so I just have to take the lead derivative of a metric with respect to certain diffeomorphism, require that the final metric also takes this form, and then solve, and you get some interesting set of results. Now, if you were BMS back in 1962, when they first did this computation, you might expect that the symmetry group that you get is Poincare, because I'm sitting very far away from everything, space is basically flat, so it's natural to expect that you just retrieve the symmetry group of special relativity, which is this Poincare. But they did not find that. Instead, they found an infinite dimensional symmetry group, and the infinite dimensional symmetry group consists of Lorentz transformations, which is expected, and instead of finding translations, they found instead what they decided to call supertranslations. It has nothing to do with supersymmetry. Okay, so what are these supertranslations? Let me just explain pictorially, which I find is to be the easiest thing to do here. So for instance, time translations, what would time translations do to the structure on Square Plus? So as I said, there's a sphere at every point on Square Plus. Time translations would simply take the sphere at a certain point and translate it, take the entire sphere and just move it forward by a certain amount in time. That's what time translations are, global time translations are. Super translations, on the other hand, are angle-dependent translations. So each point on the sphere can be translated a different amount. Some point there, some a lot. So this is what super translations was, and this is what they found to be, just coming out of the calculation, to be the symmetry group, the asymptotic symmetry group of general relativity in asymptotically flat spacetimes. So roughly speaking, the diffeomorphism, the vector field that generates this transformation, is simply given by f z bar, which is just some function on the sphere, del u, and then additional terms that I won't bother writing. But the important point is that this is an angle-dependent function, not a constant. Okay. Questions about this so far? I should mention one more thing. So something about the boundary data. Well, maybe I'll mention that right now. Okay. Okay, so these are what BMS super translations are. Now, the final step is to relate this object and that object over there. But they seem to be completely different objects right now. This is something in scattering theory, in field theory, and this is just something in general relativity. And I've done some symmetry analysis near Square Plus, so that we'll have to relate what these two are. And we'll see that after doing that correctly, these two are equal to each other in a certain sense. Okay. So to understand the relationship, as we said here, this is a theorem that has to do with scattering matrix elements. So we'll have to go back here in GR and understand what the scattering problem is in GR. So let's do that first classically, and then we'll quantize. After all of these are quantum theorems. So we'll do it classically first, and then we'll quantize. So what is the scattering problem? The scattering problem is as follows. Bondi and Metzner, BMS showed that this object CZZ and its complex conjugate, these two functions, completely describe the full spacetime in the bulk. That is to say, if I tell you what is CZZ and CZ bar on Square Plus, then you can use Einstein's equations and completely evolve the full metric back into the bulk. And there's a similar problem. So the boundary data is that on Square Plus, I need to specify CZZ, and then I can evolve backwards and find everything, what the metric looks like everywhere inside the bulk. There's an analogous problem, of course, on Square minus as well. And here you have to specify the exact analog of that, which I'm just going to call CZZ with a superscript minus. So the scattering problem is the following. Given CZZ minus, what is CZZ plus? Let me put a plus up there, right? So you give me a CZZ minus, and if I'm all powerful, I can use Einstein's equations, completely solve it in the bulk, and then go push it all the way up to Square Plus, and then I can tell you what is CZZ plus. And once I've done that, I've solved the scattering problem. Okay. But in light of these symmetries, we'll see that this is in fact an ill-defined problem in the first place, because Einstein's equations can only be solved up to diffeomorphisms. And BMS supertranslations are nothing but diffeomorphisms. So BMS, this is in some gauge, they've set up some coordinates, but as you see that despite fixing these coordinates, there are some residual gauge diffeomorphisms that preserve the structure of the metric. Thus, the scattering problem is in fact not well defined at all, because given a CZZ minus, I can only tell you what is CZZ plus up to a BMS transformation, and no more than that. So the solution is not unique. So So the scattering problem at this stage is ill-defined. In order to define it, I would have to impose certain matching conditions naturally at spatial infinity. And we'll see that once I define these matching conditions, there's a canonical identification of generators on scri minus and scri plus, so that there's a unique CZZ plus for a given CZZ minus. Okay, so that's what we'll do now. Questions? In fact, all of this analysis was done by Ashtekar, Hansen, Penrose back in 1970s, and they were stuck precisely at this point because they did not know how to canonically write down the connection between scri minus and scri plus. So the reason we can do that now is because of work by Christodoulou and Kleinerman in 1991, where they were studying a completely different problem, the problem of global stability, of global nonlinear stability of Minkowski of asymptotically flat spacetimes in a neighborhood of Minkowski space given by some Sobolev norms of some sort. But a byproduct of their analysis was precisely matching conditions across spatial infinity, and those are the things that help us completely fix and discuss the scattering problem on its own. Okay, so what were those matching conditions? Let me just write them out for you. So the CK, we call them the CK constraints. So the matching conditions are, so let me just mention, I should point out a couple of more points. Spatial infinity is singular. So when you want to typically in any asymptotically flat spacetime. So if I want to describe boundary conditions near spatial infinity, I need to be very careful in how I do that. So instead of talking about spatial infinity, I'll talk about the future of past null infinity, which I'll denote scri minus plus, and the past of future null infinity denoted by scri plus minus. Both of these are spheres, and that's what CK did also. So the constraints that CK produced are MB, the Bondi mass aspect over there, at scri plus minus is equal to MB at scri minus plus. And similarly, CZZ at scri plus minus is equal to minus CZZ at scri minus plus. Basically, they were looking at spacetimes which are entirely stable, and they showed, among other constraints, if the spacetime satisfies these constraints and some other ones, then you can solve the boundary data problem everywhere, and you get a solution in the bulk which is globally smooth, non-linearly.
Can you just explain this? I mean, I thought that CCZ would go to 0 when you're approaching I naught. So of course 0 equals minus 0 is fine, but
why would you expect that?
well, because otherwise things would blow up. I mean, so you're solving the scattering problem. If your data don't decay along scri minus, then there would be
Yes.
no.
Let me mention one more thing.
Or in other words, if you just do what Christo Kleinerman do, they start from t equals 0, and then everything does decay towards I naught.
Yes. Let me mention one more thing they did. Yes, when CK did that in what's known as the center of mass frame. So in the frame that they worked in, MB in fact at scri plus minus was a constant.
Yeah, just
And
the
CZZ was 0.
right?
However, as we've just discussed, we can do a BMS transformation. So in fact, it turns out, despite the fact that this metric looks like it's curved, because it's written, I mean, this is the flat part and there are these corrections which are curved. If CZZ takes the form dz squared of some function, where dz is the covariant derivative on the round sphere with respect to this metric, you can show that there's a diffeomorphism that brings it back to the flat metric. So it doesn't have to be 0. All it has to be is the second derivative of a function, and then the metric itself is just flat and everything is smooth. So I did not mention that second constraint. In fact, I should probably say that CZZ, what they really wanted is CZZ at scri plus minus is dz squared of a function. CZZ at scri minus plus is also dz squared of a function, some other function, let's call this C plus and C minus, and then the matching condition was that C plus is equal to C minus.
Well, that's certainly not what they did, right? But I mean, so that's your.
These are the
version
BMS
of-
extensions of what they did. Their constraints are not BMS invariant. So if you want to include BMS symmetry as being part of the phase space of data that you're considering, then you have to take their data and do a BMS transformation to it.
But then can you explain where it is coming from? This minus matching. Well, why should
This minus, yes.
Well,
I can.
why should one identify in any way things
Yes.
which happen with square minus with square plus, and why is this the reasonable way to do it?
Yes.
Because there's nothing wrong to have a scattering problem where you're mapping something to an equivalence class of something, right? So,
No, but these are,
or an
if you want to
equivalence
identify
class of
them as
something.
equivalent, it's true. But know that you wouldn't call, if I take a Schwarzschild black hole and I boost it, a boost is a diffeomorphism. But the resultant black hole, you wouldn't call as being physically equivalent to the static Schwarzschild black hole.
I would.
Okay. Well, I would. I mean, these are large diffeomorphisms. So typically, you would like to say things related by small diffeomorphisms are equivalent, but things related by large diffeomorphisms are typically not equivalent. Lorentz transformations, rotations, for instance, or boosts are large diffeomorphisms, and we typically would like to take, systems which are related by these large diffeomorphisms to be inequivalent. And supertranslations are just an extension of the boosts, the standard boosts. The boosts are in Lorentz. The supertranslations are just some large extensions of these translations. So I would like to realize them as separate physical configurations. And you can see there are charges that actually you can compute. For instance, the superrotation charge, which by this triangle that I said can be measured by their corresponding memory effect. So there is an actual measurement that can be done that would tell you whether a certain space-time has is supertranslated or not. So there's a physical measurement that you can do to distinguish between them, namely the memory measurement, and therefore I would say that they are physically distinguishable. Just to mention quickly where this minus sign is coming from is actually, that's just a technicality, but I can tell you that the transformation of CZZ plus under BMS transformations, so it's just the action of that diffeomorphism on this component of the metric you can work out, is there's one term which you expect, it's just the lead derivative because that's just f del u, but now there's a second term which is minus 2 dz squared f. And if I do the same thing on scry minus, I get f del u czz minus, but just something that comes out of the computation is that you get plus over here. So now you can see that if I start from the Christodoulou constraints in which C plus CZZ and CZZ minus are just 0, and I do a BMS transformation, then the resultant non-zero CZZ, which is appearing because of this factor only, there's a relative sign between them. So the matching condition needs to have this extra sign. So that's just a technical.
And in your first equality, you're allowing a mass aspect which is not constant.
Which is not constant.
T equals 0.
Exactly, for the same reason. The variation of the mass aspect is much more complicated, but for the exact same reason, if I start off with a constant mass aspect and do a BMS transformation, I'm going to get something which generalizes to this much.
So at T equals 0, your matrix will not follow like Schwarzschild, but like Schwarzschild with a function which then the m will not be a constant, but a
Yes,
function.
it will be a supertranslated Schwarzschild, which can be distinguished by the memory measurement. This, in fact, the fact that these additional symmetries exist is in fact very important to understand the black hole information paradox, as has recently been seen. So the statement that is usually made that black holes have no hair in this context is incorrect. If you really think about it, the statement is black holes have no hair up to diffeomorphisms, and typically we just say, okay, who cares about diffeomorphisms? But we should care about large diffeomorphisms because there are measurements that can be done. So black holes in fact have infinite number of hair given precisely by these supertranslations and also other ones, superrotations, which I'm not going to talk about right now. Okay. Questions? Okay. So I'm mostly done. Let me just write down a few more equations. And so now that we have defined these CK constraints, Now the scattering problem is very well defined. So how do we make it? What do we do then? So we start with the CZZ minus, evolve it all the way down, all the way in the bulk, and then push it on square plus. As we said, we'll only get a set of CZZ pluses up to super translations, but we choose that CZZ plus which satisfies this matching condition, and there'll be only one such CZZ plus. So this uniquely fixes CZZ plus. This gives me a well-defined notion of the scattering problem. And as we have seen, super translations form a symmetry of these scattering problems, because I can start off with one choice of CZZ minus and therefore its unique CZZ plus, and do a super translation on both of them, and I'll get a different physical solution which has different energy. So by the laws of Bernoulli's theorem, you have some infinite dimensional symmetry, and therefore you have an infinite dimensional conservation law. And these are basically these energy conservation at every angle. So scribe plus is this quasi-local surface, so that energy is conserved along every null generator as well. Okay. So we've seen at this stage everything is classical. I haven't quantized anything. So we've seen that there's to define the scattering problem, we had to introduce matching conditions, and the existence of these BMS supertranslations mean that there's a classical symmetry of the classical. There's a symmetry of the classical scattering problem. Okay, let's quantize that. Okay, what is the quantum version of the scattering problem? The quantum version of the scattering problem is that I can quantize the theory on a hypersurface square minus. I get a Hilbert space H in, which is on which I can choose a basis of what's called in states. There's a Hilbert space on square plus, which defines for us the out Hilbert space on which I can choose my states out. And the map, which takes you from the in state to the out state, is known as the S matrix operator, which is just a classical analog of evolving through all of the bulk and like finding out what CZZ plus is. So finding the S matrix is basically the problem in quantum field theory. So the S matrix is just an operator that takes an in state and gives you the corresponding out state in this kind of scattering problem that we've seen. So we don't know what the S matrix is. Of course, this is highly theory dependent, and there's many problems with infrared divergences. So it's not even clear that the S matrix exists. So for now, let's just assume that such an operator exists in the quantum theory that we're interested in. And even without knowing what the S matrix is, one thing we know is that there's a symmetry that this S matrix has to satisfy. It's just the quantum version of this symmetry over here. So what is the quantum analog of this symmetry? It's a statement that in the quantum theory there's a charge Q, and I'm going to put a subscript F to say that there's one charge for every function F that I can choose. So it's an infinite number of charges, which commutes with the S matrix. So this is just zero. This is the statement of quantum symmetry of the quantum S matrix.
And how do you know that the quantum theory has the same symmetries as the classical?
We don't. Let's conjecture it and see what happens. And we'll see that we retrieve Weinberg's soft graviton theorem. But in fact, you can also go the other way around. If you did not know anything about supertranslation, you could have started with your field theorists. You could have started with the soft graviton theorem, and then worked backwards and shown that this symmetry exists. I'm going the other way around. Let's conjecture that this is true, and we'll see that it gives you the Weinberg soft graviton theorem. Okay. So in particular, it's true as an operator statement, so it's also true when sandwiched between any two set of in and out states. So this is what's called typically a Ward identity. It's a statement about correlation functions, or rather here in this case S matrix operators. If I take any S matrix and insert this particular operator, I always get 0. And in the last 5 minutes, I'm going to convince you, I won't go into the details, the algebra is pretty complicated. I'm going to convince you that despite this funny looking statement, it in fact reduces to a soft theorem. That this charge will have two terms, a soft term and a hard term, and they will give rise to a soft limit with some of the hard terms. Okay. Any questions before I start? It's just going to be some very quick algebra. Okay, so let me just quickly explain how this works. So QF, what is the charge QF? So the first thing is to be clear about what this charge QF is. That is the charge that generates all of these symmetries. This was done back in the 70s by Ashtekar. And the charge that they wrote down is just integral of on the sphere of F and B. But this is on the sphere at square plus minus. And I'll put in a factor in there. Square root G. Okay. So this is just a fact that they worked out. You can just do this by constructing the symplectic form. Classically, you can construct the symplectic form on a hypersurface and then write down all the commutators and stuff like that and show that this object acting on the boundary data, in particular CZZ, gives you precisely the BMS transformations of CZZ. Okay. So we'll do a little bit of manipulations here. So this I can write now as, I can by hand introduce a U derivative. And there's a minus sign. So all I've done is I've just taken a term, which is a boundary term on this part of square plus, and written it as an integral over all of square plus. And of course, in addition to this, there's a second term, which is going to be the boundary term at square plus plus. This is a very simple rewriting. And for spacetimes of interest right now, we can generalize this. When you have massive particles, this is non-zero. Let's assume, just for simplicity, that all particles are massless, so they all come through square plus. It's a finite amount of time, so the final geometry is also a vacuum geometry. So this goes to 0. MB is 0 for vacuum geometries. It's non-zero when I have massive states, which I do in the real world, but that has been worked out also in detail how this affects it. I'm just going to make it simple. Now, del U MB is basically given by the evolution equation for the Bondi mass aspect, which is given entirely by the Einstein's equations. So Einstein's equation, namely, to be clear, this one, GUU is equal to TUU, completely fixes what this is, and it turns out to be of this form, F, the local Hamiltonian, TUU, plus another term, which looks like so I end up getting two terms over here. The first term is just the local Hamiltonian. So this guy, let me call it H, it simply acts on states. H acting on a state with energy omega gives you something that looks like F multiplied by omega acting on the state. And this term is another term which is a strange looking object, but there's a way to rewrite this, this is just du e to the I omega u del u CZZ, and then I can take the limit of omega going to 0. So notice I told you that this CZZ relates to gravitational radiation. Here I'm taking the Fourier transforms. As we know, the Fourier transform of the transverse component of the gravitational wave in the quantum theory becomes a creation operator that creates gravitons. And it creates gravitons with energy omega because I'm Fourier transforming the time direction. And then I take a omega goes to 0 limit in order to retrieve the object that's sitting over here. So it's a soft graviton operator. In other words, the charge that I've written over there contains a term that creates a soft graviton, and it contains another term whose action is to simply give us an overall factor multiplied by the same state multiplied by some overall factor. So that just means that if I plug it into this expression, I'm going to get two terms. One term is going to factorize into being just insertion of a soft graviton, and the another term is going to factorize as being just some overall factor multiplying the original S matrix. And it's a little bit of algebra to show. It's been done in the papers. You can read that, or you can trust me that if you work out all the details, you would reproduce exactly Weinberg's soft graviton theorem. So the crux, the conclusion is that BMS supertranslations is a symmetry of the quantum gravity S matrix, whatever that may be. The ward identity of this symmetry is Weinberg's soft graviton theorem. Thank you.
Any questions?
Can you comment on about the following? I mean, this thing is supposed to solve the black hole information paradox.
Not solve, it's supposed to modify, some of the assumptions break down.
Suppose that you just take a spherically symmetric black hole and throw in matter in a spherically symmetric way, then you start with some mass which is spherically symmetric, you end up with something which is spherically symmetric. There's an infinite number of ways of doing this, so obviously you're lost the information how you've passed from your first black hole to the second one. Nothing in these BMS transformations allows you to do something which is spherically symmetric, which is non-trivial. I mean, any BMS transformation which would be spherically symmetric is just a time translation. So there's no way you can play with these BMS transformations in this context, right? So how would this possibly even come close to address the question of information loss paradox?
Well, you're defining spherically symmetric as the Schwarzschild black hole, but if I do a large diffeomorphism of the Schwarzschild black hole, would it not be spherically symmetric?
Well, you're allowed to do whatever you want afterwards, but I told you what my process is, right? I start with spherically symmetric black hole.
Yes.
I throw in spherically symmetric matter.
If you're throwing in spherically symmetric matter, then you've kind of reduced the amount of ingoing information to just the total mass that you're sending in.
No, because I can have an infinite number of different ways of throwing in 5 kilos. First 1 kilo, then 2 kilos, then
And the short, and okay, and the radiation
none
will
of
keep
them
track of that.
will break spherical symmetry.
But I think the radiation will keep.
One of your manipulation breaks spherical symmetry.
Yes, but the outgoing Hawking radiation will keep track of that in terms of when the radiation is coming out, as given by when I'm sending it in. So every time I send in some charge, there's a soft charge that's kind of sitting on the
Well, I'm
horizon.
not questioning what happened with Hawking radiation and so forth, but I mean, what I'm just saying that BMS transformations break spherical symmetry. And there's no way you can therefore encode processes which were spherically symmetric using them. And so, well, I don't understand this now. Maybe you have a way of understanding.
Well, why do you say this? So if f is a constant, that's a spherically symmetric. And
That's the only possibility. I mean,
Yes,
the whole thing of the supertranslation is that the f is not a constant. But then you're breaking spherical symmetry, and therefore in all these processes which I've been doing, it's completely irrelevant.
Sure. If it's spherically symmetric, you have very little information since everything you're doing is spherically symmetric. And in principle, of course this is very hard. In principle, you're sending in very little information. So the only information that are coming out is the spherically symmetric part of F, and it's entirely possible that the amount of information matches up because I'm sending in a very special kind of thing, which is entirely controlled by just one number, and therefore even the outgoing thing is controlled entirely by just one number. This the zero mode of F.
But even spherical symmetry can still work on diffeomorphism. For example, even on Minkowski space-time, you can still get a non-zero mass aspect.
Sure, yeah, of course.
Yeah.
We're not questioning this, but
yeah.
I don't see how this would have anything to do with black hole information. That's my.
Well, in the presence of black holes, the final surface is not a Cauchy surface anymore. There's a horizon over here. So when you say these charge conservation laws, there's some ingoing charge, and it's not entirely collected out on prime minus. There's some of the charge that goes in, and there's a way to measure what this charge is on the horizon, and that's the statement that there's extra hair sitting on the horizon of the black hole. And when it eventually evaporates, so if it evaporates, then it goes like this, and there's Hawking radiation over here. And so this charge conservation is giving us basically infinite number of constraints that this Hawking radiation is supposed to satisfy, which immediately tells us the Hawking radiation cannot be thermal because it has to be constrained in some way. And the hope is that, because it's an infinite number of constraints in takes the originally thought to be thermal state and converts it to a pure state. None of the details have been worked out and certainly has not been solved, but it's simply that some of the assumptions that go into the proof of the information paradox are now questioned because of this entire story. That does not mean that you can't resurrect the entire argument by including these things, and therefore the information paradox might still be present.
Okay, so let's stop here. We start at what, 11?
Yep.
Okay, great. Thank you very much.